Good morning, my name is Stefano Straullu and I work for Istituto Superiore Mario Boella of Turin as an optical researcher. With this presentation, I'd like to describe a possible solution for next-generation passive optical network architecture that I demonstrated during my PhD activity and during a joint project between Politecnico di Torino and Cisco systems. Passive optical network, or PON, is a point-to-multipoint tree-like architecture composed by an optical line terminal at the central office side and by several optical network units at the customer premises. Along the optical distribution network that connects the central office to the customers, only passive optical elements, so no optical amplifiers or regeneration nodes, are allowed. Today, millions of passive optical networks are installed all over the world. In the last few years, ITOT started defining the specifications for next-generation passive optical network architecture, also known as NG-PON2. The main requirements are the time and wavelength division multiplexing approach, supporting the transmission of 4 wavelengths per direction and sharing each wavelength among users on a time division multiplexing basis, a data rate of 10 gigabit per second in downstream and 2.5 gigabit per second in upstream, and up to 35 dB of power budget, also known as ODN loss, optical distribution network loss, which corresponds to the attenuation due to the fiber and the optical splitters that a network can support. ITOT defined different classes of networks according to this parameter, from a minimum of 29 dB up to 35 dB for the highest class of PON. One of the few physical layer problems which ITOT is still working on before the final NG-PON2 recommendation release is the lack of available low-cost tunable lasers on the market with sufficient tuning range, precision and launch power to be installed at the optical network unit side for the upstream signal generation, because they should have a target price compatible with the equipment to be installed at the customer premises. For this reason, several reflective passive optical network architectures have been proposed in the last 10 years, whose key idea is to generate the unmodulated upstream wavelengths at the optical line terminal side and to modulate them in reflection at the optical network unit side, thanks to a reflective transmitter. Unfortunately, all the solutions proposed so far in literature are not fully compliant with next-generation PON requirements, in particular because their achievable ODN loss is usually well lower than the target defined by the standard due to several spurious effects, such as the Rayleigh backscattering and the very low received optical power. Indeed, when the target ODN loss is 35 dB, the useful power at the receiver's input results significantly lower than the sensitivity of the direct detection receivers available on the market. Moreover, in such an architecture, the intrinsic back reflections power can be well higher than the useful signal power at the optical line terminal receiver's input, which thus results undetectable with the direct detection receiver. The novelty of my PhD research activity starts from here, and my goal is to realize a full working reflective PON architecture prototype that satisfies the main NG-PON2 requirements for what concerns the upstream transmission. First of all, at the optical line terminal side, I replaced the direct detection receiver with a coherent detection receiver, usually adopted for long-haul applications. Of course, this is a more expensive solution, but this way I could exploit its much better sensitivity, thus targeting to higher ODN loss values. Moreover, it can be shown that the spurious back reflections after the coherent detection appear as added close to the electrical basement, thus they can be easily filtered out by an electrical and digital high-pass filtering stage, in particular if an 8-bit and B-line coding is adopted in order to minimize the impact of this filtering to the useful signal. At the same time, at the optical network unit side, I used a reflective transmitter composed by the cascade of a semiconductor optical amplifier and a reflective electroabsorption modulator in order to generate the upstream optical packets. The unmodulated wavelength coming from the optical line terminal is thus amplified by the SOA, and simultaneously the optical packets are generated by switching on and off the SOA, driving its bias current according to the time slots assigned to this optical network unit, while the upstream signal is created by driving the reflective electroabsorption modulator by pure binary modulation signal, working at 2.5 gigabit per second as defined by the standard, and finally obtaining the modulated upstream optical bursts to be transmitted towards the optical line terminal. Therefore, I realized a full working reflective PON architecture prototype for upstream transmission composed by an optical line terminal with its light source and coherent receiver, a real installed optical distribution network, and two burst mode reflective optical network units, the one under test and the interfering one, which generate their optical packets according to the time division multiple access approach. The upstream packets at the optical network unit's outputs propagate back through the optical distribution network towards the optical line terminal coherent receiver, and they are post-processed with a custom bus mode digital signal processing algorithm based on the well-known least mean square algorithm and a maximum likelihood decision in order to compute the bit error rate of each packet. I perform a full measurement campaign reporting the bit error rate of a large number of packets as a function of the ODN loss, demonstrating that the proposed setup supports more than 35 dB before reaching a standard forward error correction code threshold of 10 to the minus 3, thus satisfying the highest class requirements of the standard, even in the worst case when both active optical network units are switched on. I published these results to Optics Express journal and to the most important international conferences on optical communication, ECOC and OFC. The proposed architecture was then finalized, increasing the upstream bit rate to 10 gigabit per second, envisioning a possible next-generation PON longer-term evolution case, and replacing the expensive external cavity laser at the optical line terminal side with a cheaper commercial distributed feedback laser, satisfying also in this case the highest class requirement of 35 dB if the external cavity laser is used, and the intermediate class of requirement of 31 dB if the distributed feedback laser is used. Again, I published these results to ECOC conference. To summarize, with this work I demonstrated that the proposed reflective burst mode passive optical network architecture fully satisfies the main requirements defined by NG.2 standard for the upstream transmission, even without the expensive tunable laser at the customer side. Thank you very much for your attention.